Hello students, welcome back. I am addressing you today through this virtual class, and the reason is known to all of you because we are now not being able to meet at our well coveted PH1 and PH2 at the physics department of Sri Rampur College. I hope all of you are doing fine, staying at home, not going out without any necessary reason, and keeping healthy. And at the same time, I also hope that you are all doing some studying. So today I am going to discuss with you the second part of interference, namely Young's double slit arrangement and Fresnel's biprism arrangement. We have discussed how two light waves superpose on each other to give an interference pattern. In the present discussion, we'll be delving into the type and size of fringes formed in an interference pattern. That is, we have discussed earlier that how interference pattern is formed. Now we are going to find out what will be the fringe width and other necessary things and how to derive a formula for fringe width. As I told you, we will be discussing two scenarios. One, the Young's double slit arrangement, and two, the Fresnel's biprism arrangement. But before that, a brief recapitulation of the last class. We have learned from the last class that two waves of constant phase difference superpose on each other to give interference. Now this constant phase difference is very important. When two waves coming from two sources maintain a constant phase difference, they are called coherent. If they cannot maintain this constant phase difference and the phase difference keep changing with time, then no sustained interference pattern can be obtained. Now, previously we have seen some case where one primary source is divided into two secondary sources. In the previous case, we did it in a particular way. Actually, this division of a primary source into two secondary sources, and in doing so, achieving two coherent sources, this whole thing can be done in two ways. One, by division of wavefront, and two, by division of amplitude. What we discussed in the last class, that is placing a barrier with two apertures in front of a primary source such that the two apertures are equidistant from the primary source. That was a typical example of interference by division of wavefront. Division of amplitude, however, will be taken up later when we deal with Newton's rings. A little more on the last class. Now, as I told you, we had produced two secondary sources S1, S2 from a primary source S. This was the diagram. As you see, the primary source S is placed behind a barrier with two slits S1, S2, which are at a distance d from each other. And from this slit arrangement at a distance capital D, the screen was placed, the screen X and Y. S1P is X1 and S2P is X2. Now we are interested in finding out the resultant disturbance at P. Now according to superposition principle, the resultant disturbance at P is Y1 plus Y2. Remember, Y1 is the disturbance at P due to source S1 and Y2 is the disturbance at P due to source S2. Superposition principle says that when these two waves superpose at P, none of them affect each other, they just add up. Now the disturbance at Y1 is represented as A1 exponential I omega t minus kx1 and Y2 A2 exponential I omega t minus kx2. We just add them according to superposition principle, and doing some mathematical manipulations, we get this expression, that is y is equal to exponential I omega t a1 cos kx1 minus I sin kx1 plus a2 cos kx2 minus I sin kx2. Since this is a complex number, we will also find its conjugate, which is given as this. Now, we would like to know what is the intensity at P. So, according to the definition of intensity, I is y star y, and this is the expression for intensity. All these things we have taken up in the last class. We are just recapitulating it. I is equal to a1 square plus a2 square plus 2a1 a2 cos k x2 difference x1. Now remember this difference sign. I have emphasized upon this in the previous class. So as is obvious from the above, the factor cos k x2 difference x1 controls the intensity. As you know. Now case 1, when the difference of x2 and x1 is even multiple of half the wavelength, we have seen that in that case the intensity becomes maximum, that is a1 plus a2 whole square. There is another case, that is case 2, when the difference of x2 and x1 is an odd integral multiple of lambda by 2. In that case we get the minimum intensity, that is a1 minus a2 whole square. One last point, when the amplitude of both s1 and s2 are same, let's say that the apertures are of same width, and hence the light coming out from them is of same intensity. In that case, the maximum intensity after interference will be 4a square and the minimum intensity will be 0. Now, Young's double slit experiment. What we have done in the superposition principle, we have recapitulated. Remember, these were the things we have done in the previous classes. Now we go straight into Young's double slit experiment. In Young's double slit arrangement, as we'll see that Young's double slit arrangement is not much different from the diagram below. That means the diagram we have been dealing with. The same division of wavefront method we are taking up here. Two coherent sources from a primary source are produced. That means, and we do it with two identical slits so that A1 is equal to A2. This is the diagram, the same diagram here. S1 S2 is equal to small d, S1 M is equal to S2 M is equal to d by 2 when M is the midpoint between S1 and S2. XY is the screen on which interference pattern appears. We are interested about the point P. Capital D is the distance between the slits and the screen, or the center of the fringe pattern. The arbitrary point P on screen XY is at a distance x from O. So we can easily see by applying Pythagoras theorem that S1P whole square is equal to x minus d by 2 whole square, and S2P whole square is equal to x plus d by 2 whole square. So the difference of S2P whole square minus S1P whole square will be twice xt. Now S2P whole square minus S1P whole square, applying a square minus b square formula, we can break it up into two factors like this. Now here is one assumption. S2P and S1P both have been taken to be equal to capital D. Why is that? Because small d is very, very less than capital D. Hence, we can, to a good level of approximation, consider S2P and S1P both equal to capital D. So if we do that, we get twice D into S2P minus S1P is equal to 2xD. So finally, we have S2P minus S1P, that is the path difference, x2 minus x1 is equal to small x small d by capital D. Remember, though x2 and x1 are denoted to give the distance of the arbitrary point from the two virtual sources, small x is basically giving the distance of any arbitrary point from the center of the interference fringe. So we have finally x2 minus x1 is equal to small x small d by capital D. Now, what happens if we are considering an nth order bright fringe at P? We have x2 n minus x1 n is equal to 2n lambda by 2. So we have xn small d by capital D is equal to 2n lambda by 2. Now, if we have n plus 1th order bright fringe, then xn plus 1, that means the distance of the n plus 1th order bright fringe will be multiplied by small d and divided by capital D will be 2 into n plus 1 by lambda by 2. So, in between these two bright fringes, there will be a distance xn plus 1 minus xn that will be given by small lambda capital D by small d. Now, if we consider dark fringes, what will happen? We will just get xn small d by capital D is equal to 2n plus 1 into lambda by 2 for nth order dark fringe. For the n plus 1th order dark fringe, we will have xn plus 1 small d by capital D is equal to 2n plus 3 lambda by 2. And if you are interested in finding out the distance between two consecutive dark fringes, we see that in between them, the distance is lambda capital D by small d. That is the same thing we found in case of bright fringes. Thus, fringe width is lambda capital D by small d. While considering nth and n plus 1th order bright fringe, whose fringe width was actually determined? Well, likewise, while considering nth and n plus 1th order fringe, whose fringe width was actually determined? Try to find the answers to the above two questions. Whatever the answers, what you should keep in mind is that the fringe width is always lambda capital D by small d, irrespective of the type of fringe. The case of Fresnel's biprism is not much different from that of Young's double slit experiment. Here, once again, two coherent sources S1 and S2 from a primary source S is formed. Now, this is the diagram of Fresnel's biprism arrangement. You see P is a biprism. It is something typical of a biprism, quite different from other typical prisms. As you see, the vertex angle of P is almost equal to 180 degrees. It is generally near about 179 degrees. Light from S is, that is the source S, is made to fall equally on the two halves of P as shown. The incident wavefront divided into two after refraction from the two halves of the prism give rise to the virtual sources S1, S2. So here the scenario is same as the Young's double slit experiment, because we are getting once again two virtual sources, two sources S1, S2. Just in this case, the two sources are virtual. So what will be the fringe width? It will have the same formula, lambda capital D by small d. But how to find D? This is a big problem, at least it appears to be a big problem at this juncture, because S1 and S2 are no more real sources as it was in case of Young's double slit experiment. They are virtual sources. Experimentally, this is done by placing a lens between the eyepiece and the biprism. That means how to find D? We just place an eyepiece between the we just place a lens between the eyepiece and the biprism. Let's say that the focal length of the lens is small f. The distance between the eyepiece and the biprism is taken to be greater than 4 times f, and you know what happens then from your knowledge of +1 and +2 physics. Now this is the diagram. As you see, this is the biprism, and this is the biprism. I'm sorry. This is the biprism, and here is the lens, and the distance between the biprism and the eyepiece is 4 times f, small f, when smallest f is the focal length of the lens. As you know, there will be two positions of the lens, L1 and L2, as shown in the diagram, for which we will get images of the two slits on the eyepiece. The only thing is the distance of the two slits will appear different for the two positions of the lens because they will be having different magnifications. Now C1 and C2 are respectively the distances between the two virtual sources for two conjugate positions of the lens. The distance d is given as small d is equal to root over C1 C2. Once we have d, it is easy to find the fringe width using the formula, that is fringe width is equal to lambda capital D by small d. That means the only problem we were facing was to find small d in case of Fresnel's biprism because the two sources were virtual. That's why we took this special arrangement and found small d, and the rest becomes straightforward. You just put the value of small d and you get the fringe width. Now that is all about Young's double slit and Fresnel's biprism arrangements. Next class we will take up two more topics before we move to the interference by division of amplitude. So that's all. Feel free to contact me. You all have my phone numbers. If necessary, you can have my emails also. Just call me and I'll give you my emails. So till we meet again, at least virtually, keep healthy, keep studying, and keep smiling till you meet and chat like this again. Thank you.